So in today's lesson, we are going to be starting in chapter 1, and our first topic is going to be over functions. Now, we've seen functions for a long time, since back all the way to pre-algebra, but again, we just want to review, make sure that we're all kind of on the same page with our definitions and things like that. So one of the hard things in general about math is that a lot of times we know a basic definition, but we don't know the technical definition. So when we're looking at functions, a lot of us can think about and know what I mean when I say that, but we don't know the actual math definition of it. So when I'm talking about a function, most of us know that we're talking about input and output. And it's going to be a relation between our input and output. But the key, or maybe the way that you've heard about it in the past, is that it has to be pass that vertical line test or the pencil test. Which is okay when we're thinking about it, but we don't want to write that out when we're putting the definition. So we want to write, it is going to be a relation between two sets that assigns one x value from the first set to exactly one y value is the second set. Now, I use x and y because that is the general notation that we're used to seeing. However, it could be a and b or r and s, which is why I kind of put them in quotations, because x and y is what we generally see, but we're technically just looking at one value from our first set to one value in our second set. Now, most of the time, y'all are used to seeing our functions algebraically, which means with equations and variables and all of that stuff. And we're pretty comfortable with that. However, in mathematics, we need to be able to use all of our representations and be able to switch between the two, or the four, actually, sorry. So we're used to seeing it algebraically. The other one that we're pretty comfortable with is graphically. But we do have two more. There is a table, which when we first started learning about functions, we did the t-chart, and so we've seen tables before, but as you continue on, you use them less and less, but we still need to be reminded about how to use them and what they mean. And then the last way is verbal. Now, when I say verbal, I don't mean actually like me talking out loud. Sometimes it can be a written statement, but using words to describe a situation. So in our first example, it says determine whether the relation represents a y as a function of x. And it gives us a couple of different representation here. So on part A, it says the input of x is the number of representatives from a state, and the output value, y, is the number of senators. Now, we're going to need to do a little bit of a history lesson, or government, to help us remember what our number of representatives and our number of senators are based upon. So hopefully, we remember that our numbers of representatives from each state is going to be based upon population of that state, which means that it's going to be different for different states. Now, for our number of senators, each state gets exactly 2 senators. So we need to think about this, hopefully, in terms maybe of a graph. It might be able to make it a little bit more clear for us. So if we were to graph this, notice that my x values are going to be all positive, which means it's going to be on the right side of my graph. And they're going to go from 1 all the way up to whatever the largest one is, like 100 or 200. I'm not sure. But all of my outputs or my y values are going to be at 2. So notice that this would pass our vertical line test. So it is a function. Now, if we did it the opposite way, though, and said that our input values were our number of senators and our output values were our number of representatives, notice that our graph would switch to be where all of our inputs were 2. And so we would get a vertical line instead, and so that would not be a function. So looking at our next input and output, we have a table, which is fine, we can do that. And the biggest thing here that I'm going to look at all of my inputs, and the first thing that I should notice is that I have 2 2s. And then we should notice that I have 2 different y values associated with those inputs. I have a point at 211, and I also have a point at 210, which means that this is not going to be a function because I have more than one y value for one x value. And on our last one, it's pretty easy to see that this would pass my vertical line test. I don't have any points that are kind of on top of each other as far as on the same x value. All right, and then lastly, again, this is the representation that usually we're most familiar with, which is our algebraic. However, some of us still need to be reminded a little bit about how we can figure out if something is a function or not. So usually the way that we want to write our equations is with our y solved. So in this case, I would subtract my x squared over, and I would get y equals negative x squared plus 1. And notice that if I were to plug, say, 1 into x, I would square it and then take a negative, add a 1, and I would get 0. There's no way for me to get out a different number besides 0 if I plug in 1. So this would be a function. Again, another way, if it's helpful for us to look at this equation, this is going to be a parabola that is facing down, that has been shifted up 1. And we'll get into graphs later on, but if we were wanting to check it graphically, that is what our graph will look like. Now on my next one, again, usually we want to solve for y, so I'm going to add x over. And then notice we have a squared, so we need to take the square root of both sides in order to solve for y. However, remember that when we take the square root of an equation, we have to add a plus or minus in front. So notice that if I were to say plug in 3 for my x, I would do 3 plus 1 gives me 4. And so then I would get 2. But because of that plus or minus, I get plus or minus 2. So I have one x value that's going to 2 different y values. So it would not be a function at that point. All right, next up we want to evaluate. So remember, evaluating a function just means to plug something into that function to find a value, which is kind of where that key component of value comes in evaluate. And we can do that with numbers, We can also do that with variables, and we can do that with expressions as well. And we're going to look at an example of all three of those. So notice that our function is g of x equals negative x squared plus 4x plus 1. And they ask us to evaluate g of 2. So again, remember that all evaluating means is I'm going to replace every value or variable with what they give me, which is going to be 2. And then I'm just going to use my order of operations. So we need to do our exponents first. So 2 squared gives us 4. Notice that that negative is not included in the squared. I don't have parentheses. So it's not negative 2 squared. It's just 2 squared, and then I'm sticking a negative on top of it. So then I have 4 times 2 gives me 8, and then plus 1. So we have negative 4 plus 8 gives us 4, plus 1 gives us 5. And so in that case, our answer is just a number. It's 5, and that's fine. But our answers don't always have to be numbers. So notice on part B, they asked me this time to find g of t. So instead of plugging in a number like 2, I want to plug in a letter. And it's going to work the same way. Anywhere that I see an x, I'm going to put a t instead. So I have negative t squared plus 4t plus 1. Now, because I don't have any like terms, that means that there's nothing that I can simplify. That's just going to be my answer. So then moving on, my last expression that I want to evaluate is g of x plus 2. So notice this time I have both a variable and a number, which means that I have to plug this x plus 2 into anywhere that I see an x. We can kind of think of it like copying and pasting. I don't want an x there anymore. I want to paste the x plus 2 over it and replace it. So instead of an x, I'm going to write x plus 2. But my negative is still there and my squared is still there. Then I'm going to add. And again, my 4 stays the same, but instead of an x, I'm going to again copy, paste my x plus 2 in its place. And then I have a plus 1. And so then we just need to simplify. So I'm going to multiply out my x plus 2. Now, please remember that we cannot distribute a exponent if I have addition in there. What this actually means is we have x plus 2 times x plus 2. And so we would need to multiply it out. Some of you are used to calling that FOILing. That's fine as well. But we do need to make sure that we are not trying to distribute that squared. So we would end up with x squared. Then we would get plus a 2x plus a 2x. So we get plus 4x. And then we have 2 times 2, which gives us 4. Again, distributing our 4 to our next parentheses, and then distributing that negative. So we have negative x squared minus 4x minus 4 plus 4x plus 8 plus 1. Our last step is to simplify any like terms. I have a negative 4x, a positive 4x, so those are going to reduce to 0. And then I have a minus 4 plus 8 plus 1. So negative 4 plus 8 gives us, opposite. It gives us 4, and then plus 1 gives us 5. So that would be my answer. I don't have any other like terms, and so I'm done. Moving on. It says find all the real values of x such that f of x equals 0. So notice what they're asking us to do here is to find what x values make my whole function 0. So I'm not replacing the x this time, I'm replacing the f of x. And then we need to solve. On our first one, we just have a linear function, and so we're going to solve it using our normal linear operations. And so I would subtract 10, then I'm going to divide by a negative 2, and so I get a positive 5. So I know that if I were to plug 5 into my first equation, I would get 0 out. Now we want to do the same thing with our second one. However, we need to be a little bit careful. So notice that I now have a quadratic function, which means that I can't just start subtracting 6, divide by 5, because then I have this x squared, and we have two x's on that side, and we can't combine them. So remember, with our quadratics, our first goal is to always factor it if it's possible. So we've covered factoring now in our review section. So hopefully we remember I'm looking for two numbers that multiply together to give me 6, that add together to give me a negative 5. And those two numbers are going to be negative 2 and negative 3. So in this case, it does factor. If it didn't factor, remember that we have our quadratic formula, and we would have to use that to solve instead. But in this case, it does factor. So remember, once I factor it, I can take each of those factors and set them to 0 separately. And now they're both just linear equations, and we can solve them using those opposite operations. And so we get that x equals 2 and x equals 3. All right, next up, we want to look, okay, where does f of x equal g of x? So they give us an f of x, they give us a g of x, so we have two functions, and we want to know where they equal one another or where they intersect or cross each other. And the big key here is that I have an equal sign, and so that's all I'm going to do is I'm going to replace what they give me for my equation for f of x into the left side, and then I'm going to replace what they gave me for g of x into the right side. And then we're just going to solve. So I have x's on both sides. So I'm going to need to move them all to one side. So I'm going to add an x squared over. So I get 2x squared. I'm going to subtract a 3x. And then I'm going to add 1. So this time we also have a quadratic. So remember, our first goal is to factor. But I need to do a times c this time since I have a leading coefficient of 2. So we were looking for two numbers that multiply together to give me 2, that add together to give me negative 3. So notice that our two numbers would be negative 2 and negative 1. Then factoring by grouping. We get x minus 1 and 2x minus 1. And again, then we can set each of those factors, separately to 0. So we get x equals a positive 1 and x equals a positive 1/2. So then on part B, again, we're just using the two equations that they gave us and replacing that on the left and right side. We move our x squared over. I get 2x squared minus x. And then if I move my negative, or if I subtract to get my 2 to come over, I would end up with negative 3. So this time we're looking at 2 times negative 3 gives us a negative 6. So we're looking for two numbers that multiply together to give us negative 6, that add together to give us a negative 1. So we would have 2x, so positive 2, and a negative 3. So again, then I'm going to factor by grouping. So notice here that I am using my factoring to help me solve. My factoring is not my goal. So if we're still struggling with the factoring, we need to make sure that we're coming in to get extra help on that, because we can no longer spend just a ton of time on the factoring. We need to be pretty proficient at factoring and be able to use it to help us solve for things. So in this case, we factored it, and then we set each of our factors equal to 0, and we get x equals negative 1 and x equals 3/2. Now, in our last example, we're going to talk about domain. Now, domain is important not only when we're looking at a graph, but also when we're looking at things given to us, different representations. So in this case, we're given a couple of different representations. So on our first one, they just give us a list of points. So remember that our domain are going to be our x values. So in this case, since I'm just given a list of points, I'm just going to list all of my x values. And so that would be my domain for A. Now on part B, hopefully that looks kind of familiar. we have 1 divided by x plus 5. It's a rational. And remember that with rationals, our denominator cannot equal 0. So if I were to set x plus 5 cannot equal 0, notice that x cannot equal negative 5. Now, there are 2 different notations that we can use. There's set builder. So in this case, I have all real numbers. That's what the double backed R means, such that x cannot equal negative 5. So basically, I'm saying it can be any number as long as x doesn't equal negative 5. And that is set builder notation. The other notation is interval notation. And that's with the parentheses and the square brackets. So we are going to say that it goes from negative infinity to negative 5. And remember that a parentheses means that it does not equal. So there's not an equal to bar there. And then we're going to union, and then we're going to have negative 5 to infinity. So again, basically we're saying I'm going to include all of the numbers, even anything that's super close to negative 5. We're just not including negative 5. On C, notice that I have V equals 4/3 pi r cubed. But they tell us that this is the volume of a sphere. And that's really important because technically, if we just had this equation, r could be any number. I can plug anything into r, multiply it. There's not any restrictions on it. It's just being cubed. However, because I'm saying that the v equals the volume of a sphere, that means that my r equals the radius of a sphere, which means that I can't have 0 or a negative in my r. So for my domain, I'm going to say that it's all real numbers such that r has to be greater than 0. Or the other notation would be 0 to infinity. And then lastly on D, remember with our square roots that everything inside of our square root has to be greater than or equal to 0. So in order to be able to figure out our restriction on x, we would need to solve that inequality. So I get that x has to be less than or equal to 4/3. So again, the notation that we would use, we can either put a double backed r, or if it's a pretty standard letter, like x, you can put x such that x is less than or equal to 4/3. So this x basically represents the same thing. I'm saying I can plug any number, any real number, in for x as long as it's less than or equal to 4/3. And again, our other notation for our interval notation. So because it can be anything smaller than, that means it can go all the way to negative infinity. It can get smaller and smaller and smaller and smaller forever. And it can go all the way up until I get to 4/3. But it can't be anything bigger than that. However, this time, notice that we do have an equal to bar. So it can equal 4/3 this time. So instead of the parentheses that we've been using, we're going to use that square bracket because that means that I have an equal to sign, or it can equal 4/3. So just keep in mind your restrictions and your real world applications like in part C when we're thinking about the domains of our different types of functions.